Lesson number 13 is on the laws of thermodynamics and mechanical energy. So first of all, you need to know these two laws. These are things that you will get again and again. You'll be asked what they are. You'll have questions about how to use them, what they mean, give an example. So these are really important to know. There's two laws of thermodynamics. The first one is energy cannot be created or destroyed, only converted from one form to another. It can't just be created spontaneously, and you can't destroy energy. It goes somewhere. So for example, in that middle picture there, it's a picture of a bomb. The energy started with the fuel or the components of the bomb, and the resulting energy is the heat and the light coming off of it. It's the same when people eat something, a fuel, let's say an apple. Eat an apple, that energy goes from the chemical source, which is the actual fruit, into your body to be used for something else. Now the second law of thermodynamics states that no process can be 100% efficient. Some energy will always remain in the form of thermal energy. So basically what that's saying is that the second law of thermodynamics means that nothing can be 100% efficient. No vehicle can be 100% efficient. Humans actually are around 36% efficient at the very best. The rest of that energy is given off as waste. And in most cases, the waste energy is thermal energy or heat energy. It's the same thing with an engine. An engine that's burning fuel, the actual energy that goes from the fuel to the usable form or movement, that's the whole point of putting the fuel in the car, is very, very small. That's why when you go on a long trip somewhere, let's say you get in your car, going shopping in Calgary, I'm going to hit up the Lulu store. If it's the wintertime or even the summertime, once as you get to Calgary, you put your hand on the hood is hot. Okay, that thermal energy or that heat, the reason why the top of that hood of your car is so hot is because of the excess waste that's given off during that energy transformation from fuel or the gas to the movement or to making the engine work. Okay, so the energy that actually does the preferred task is called the useful energy. The energy that is given off as waste is the waste energy or thermal energy. When we're talking about the total energy of a system, however, we talked about potential energy, we talked about kinetic energy. Now, kinetic and potential energy are very closely related in most situations. For example, a roller coaster. On the top, before a dip of a roller coaster, you have potential energy. At the bottom of the drop, you have kinetic energy. Okay, now, the change there, the combined of the two, is a type of energy called mechanical energy. Mechanical energy is defined as the sum, or sum means adding, of the energy due to motion and the energy due to position. The best one that we usually use, and this is one that helps me remember what it is, a roller coaster. Roller coasters don't have engines. They run on mechanical energy. So you either have lots of potential energy, lots of kinetic energy, or you could have both. At the very top of the roller coaster, you have mostly potential energy, energy of position. At the bottom of that dip, you have mostly kinetic energy or energy of motion. But in the middle of the roller coaster, in the middle of that drop, you have some kinetic energy because you have gained some speed, but you also still have some potential energy. Now, the total amount of energy in the whole system usually will never change. In the case, let's say it's 100% efficient, the amount of potential energy at the top will be the same as the amount of kinetic energy at the bottom. Okay, it's also the same as in the middle. In the middle of a roller coaster, if you add the potential energy at that point and the kinetic energy at that point, they should equal to the total amount of energy that we had before. Okay, so the law of conservation of energy, also something good to know, states that the total amount of energy in a given situation remains constant. So, energy is converted from one form to another, but the total energy, or mechanical energy, never changes. Okay, so for example, kinetic energy is converted to potential energy and vice versa. So the change in kinetic equals the change in potential. At the top of your roller coaster, you have high potential energy. So for example, 1,500 joules. So let's say you're stopped at the top, you're not moving. 0 joules of kinetic energy. Once as that car goes down that drop, at the bottom, it no longer can go down any further, so it no longer has any potential energy. But it has maximum kinetic energy. So all of the energy that was 1500 joules is now energy of movement, the kinetic energy at the bottom. Okay, now let's say it goes up a little bit to our third position here. You gained a little bit of potential energy, but you still should be going fairly fast. Okay, you're not stopped at the top of this little dip. So if you add those two together, 400 plus 1100 is still equaling the same, 1500 joules. And again, this is in the case if this roller coaster was 100% efficient. So let's do a couple of examples that you might see on a test or on an assignment. This picture right here is a pendulum. What a pendulum is a ball starts at the top of its swing, just like in a grandfather clock. You let it go, and it will travel down from potential energy at the top to kinetic energy at the bottom. Now the kinetic energy then will continue the swing until it stops at the very top. So in the first position here, you have all potential energy. At the very bottom of your swing, you can't fall down anymore, so you have all the kinetic energy at the bottom. And then once it goes back up to the top again on the other side, you now have converted all of your kinetic energy back to potential energy. So some questions that you might see. For A, how much potential energy is in the ball at the top? Okay, so on their side here, you'll notice we have mass and our height. They're both in the correct units. We can assume that our gravitational acceleration is 9.81. So how much potential energy is in the ball at the top? We have our mass and our gravity and our height, so we can use our potential energy formula. Because at the top of this swing, all of the energy is potential energy. We write down our formula, mass times gravity times height for 1 mark. For a second mark, we show our work. So our work is going to be substituting in those numbers. 4 times 9.81 times 3.5. Do your multiplying there. You end up with 137.34. Now we have 3 significant digits for our mass. We have 3 significant digits for our height. Remember, we do not include our gravitational acceleration when we're worrying about significant digits. So our answer is going to have 3 significant digits. 137 joules. Now for B, what is the total energy of the pendulum system? Well, at the top of the swing, we only have potential energy. We do not have any motion yet. So at the top here, we've already calculated our 137, so it's going to be the same. Our potential energy at the top point there is 137. We already just calculated that. There's no motion yet, so the kinetic energy is 0. Add those together, and our answer for this one is the same number, 137. For C, what is the speed of the ball at the bottom? So the speed would be V, right? Now, V we find in our kinetic energy formula. So we have our energy right here now. We also have our mass from before. Now we can calculate our speed or our velocity. So we write down our formula. We substitute in our numbers. We do our multiplying and dividing first. Now all we have to do is take the square root of 68.5, and that's going to equal 8.276 for a final answer of 8.28 meters per second. So let's do a couple of practice questions, and then we'll try it out on your own. So for the first one here, a ball rests on top of a shelf. The ball has a mass of 2.50 kilograms. And the shelf is 2.30 meters high. So we have our mass, we have our height. What's the total energy of the ball shelf system? Well, it's at the very top. It's all potential energy, so we can just calculate our potential energy at the top. So So we don't know what our energy is. Our mass is 2.50, our gravity is 9.81, and our height is 2.30. So we write down our formula, we substitute in our values, and we end up with 56.4075. We have 3 significant digits for our mass and 3 for our height. We don't count our gravitational acceleration, so our final answer should be 56.4, or in joules. For the second part, what amount of kinetic energy will the ball have right before it hits the ground? It's going to be the same as the potential energy at the top, so 56.4 joules. For number 3, what will the speed of the ball be right before it hits the ground? So we're going to use our kinetic energy formula, and we're going to solve for speed, or V, just like we did with our previous question. So we have our energy, we have our mass, we have to solve for V. We write down our equation, we substitute in our values, we do our multiplying and dividing first. So 45.12, the square root of that, with 3 significant digits, ends up to be 6.72 meters per second. Now for this question, 4 parts to it. There's this slide and the next slide, so please make sure that you have your information already written down for when the next slide comes up. Okay, how much work? So when it says work here, the units that represent work are joules, so we're looking for a type of energy. Was required by a 65 kilogram person, that's our mass, to get a height of 6 meters. And that's our height. So we're looking for something that ends up in joules. We have a mass, we have a height, we know this is on Earth, so it must have the same gravity, so we can use our potential energy formula for this one. Let's write down what we have. So energy equals mass times gravity times height. And substitute in our values. We end up with 3,825.9. Now there's only 3 significant digits in the question, so we can only have 3 significant digits afterwards. So 3.83 times 10 to the third joules. Now for the second part, what is the total energy of the person as he holds himself still at 6 meters? Well, that height is the same as in the above question. So the total energy is going to be the same. It's the total amount of potential energy. 3.83 times 10 to the third joules. So now, remember these numbers for the next slide. What speed will the person be going when they fall to the ground? The letter that represents speed is V. We know our energy from the last problem, or the last question. It's 3.83 times 10 to the third joules. And our mass is also the same from last time, 65 kilograms. So we can use our kinetic energy formula to solve for the speed that he'll be going when they fall to the ground. So we write down our formula, where we substitute in our values. We do the multiplying first. We square root that number, and we end up with 10.9 meters per second. Now for the last part, what is his speed when all of the potential energy is now kinetic? When he's at the top, that he has all potential energy. When he's all the way at the bottom, it's all kinetic energy. So what is his speed? The speed will be the same. Now for your homework, I'd like you to complete the next 3 questions. Please make sure you write down the questions and your formula, work, and answer. While you're going through this, it's going to be the exact same format as the practice questions on the board, but you just have to do them in 2 steps. Your 60 meters is your height, your 600 kilograms is your mass, and it asks how fast will the cart be moving. So it's asking for the speed. What you need to do is calculate your potential energy first, then you're going to use that energy in your kinetic energy formula to solve for speed. Please show both steps clearly. Please do not round anything until the very end.